Hello and welcome to Empowered Learning. This is the second part of the definition of a derivative concepts videos. And so I wanted to start off with another example of how we can actually use the difference quotient to help us to be able to find out the derivative of a particular function at a particular x value. And so the way that we are interpreting the derivative here is as the slope of a tangent line. And so for this example, we're asked to find out what f prime of 2 is, which is what is the derivative of this function at x equals 2, and use that quantity to find the equation of the tangent line to this function f of x at the point 2, 2. So the first thing that we want to make sure that we recognize here is that when we say this, we're really trying to find the slope of the tangent line at a specific point. In this case, the point is 2, 2 on the graph of this function. So, of course, we have several different forms of the difference quotient we could use. The two most popular are this form and this form. And we will be using this form here because it'll be the easiest to deal with because we're asked to find the derivative of a function at a particular value. And so this is like the a that's right there. So it makes it much easier to deal with that way. So we know that to find the slope of the tangent line, we need to be able to find the limit of the difference quotient, as in this case x approaches a and our a is 2. So we're going to look at it this way. And so these should be big F's, not little f's. So go ahead and make that. So now we'll just work on figuring out what this is actually going to look like. And then after we simplify this part, then we'll just put it into the limit notation as x approaches 2. So we know that f of x is just 5x divided by 1 plus x squared. And we also know that f of 2, according to what we see here, is just 2. So we'll take that and divide that by x minus 2. Now, using algebraic techniques here, we know that this is like that over 1, and we need to make a common denominator. So to do that, we need to multiply numerator and denominator by 1 plus x squared. So 1 plus x squared here. And so that'll end up being just 5x minus 2 times 1 plus x squared, all that over 1 plus x squared, all that over x minus 2. And that's a 1 there. Okay? So if we keep on going, we distribute. And so that'll be 5x minus 2 minus 2x squared. And here this will be just 1 plus x squared, that times x minus 2. And so from there, we keep on going. Let's go ahead and factor out a negative out of the numerator. So if we do that, then of course this will be 2x squared minus 5x. That'll be plus 2. And we'll have the 1 plus x squared and the x minus 2 here. So now if we factor our numerator here, we'll see that we get 2x minus 1 times x minus 2. Of course, if we keep our denominator the same, you notice here that we have a common factor of x minus 2 in the numerator and denominator. So that reduces to 1. And so now what we see is that this difference quotient here is algebraically can be rewritten in this form. Okay, what this means in terms of the limit, whenever we put it in here, we're going to say that the limit of this as x approaches 2 is going to act just like this expression or this function as x approaches 2. And so now we know that we're in a good place here because if I were to plug in 2 into this x right here, I know that I wouldn't get 0 in the denominator. So now I'm where I need to be. So we know that the slope of the tangent line, which is the same as f prime of 2, or the derivative of that function of 2, is equal to the limit as x approaches 2 of our difference quotient, but now that's going to just be the same as what we have here. And all I have to do now, since this is a rational function and 2 is in the domain of that rational function, I can just plug in 2 or evaluate the rational function at 2. That's the more proper way of saying it. And we see what we get. So here we have 4 minus 1 is 3. And we have 4 plus 1 there is 5. So we see that the slope of the tangent line for this particular function here at 2 is going to be negative 3/5. So all that's left to do now is actually find the equation of the tangent line. And so that can be done quickly because all we need to do at this point is just plug everything into our point slope form and figure out what final result will be. And so we'll use x1, y1 here for our points. So if we do that, that'll be 2, negative 3/5, and 2 there again. So from that point, we can just simplify. So I'll just go ahead and work everything out. And then we'll move on to the next example. We got 3/5 x plus 6/5. And then, of course, if we add 2 to both sides, 2 in terms of 10 is the same as 10 divided by 5, same as 2. So there, that would be y equals 3/5 x. And of course, 6/5 plus 10/5 is 16/5. So that would be the actual equation of the line that goes through this particular point on the graph of this function here. Okay, so now let's move on to the second part of this question. So we're asked to illustrate what we found in the first part, which is taking the tangent line, and we want to graph that along with the actual curve that we were originally given. So to make sure that this is clear, we want to take this function, which is f of x is equal to 5x divided by 1 plus x squared, and we want to also graph that with the tangent line, which was negative 3/5 x plus 16/5. And I think I remember that correctly. Let's go back up here. Yep, that's what it was. All right, so what we want to do here is actually graph both of these at the same time. Now, you could use your calculators to do this if you want. I'm not going to necessarily do that. I'm just going to kind of look at the function and sort of guess with its properties what it will be. So if you're going to use your calculators, this would be the suggested window that I say that you use. But for the function, let's see, 5x plus 1 over x squared, first thing I know is that there is an x-intercept at the origin. We also know since the degree of the numerator is smaller than the degree of the denominator, so the degree of the numerator is 1, the degree of the denominator is 2, we know that there is a horizontal asymptote at y equals 0. So we know that. We're also given that there is the point 2, 2 on the graph, so we'll go ahead and place that point there. And the other thing that I want to mention here is that if we test to see whether this function is odd or even, we'll find out here that this function looks like it is going to be odd. And so here that'll be a negative 5x 1 plus x squared, which is the negative of what we have here, so that function is indeed odd. So because of that, we know that since we have the point 2, 2 on the graph, we also have the point negative 2, negative 2 on the graph as well. Okay? And so some of the other things that we know here is that, of course, we have this horizontal asymptote, so our graph is going to eventually have to kind of go like this here, and we know that since it's odd, this part is going to be above the x-axis, and this part will be below the x-axis. So we could plot some other points, but we have enough going on here to kind of know how this is going to look. And so let's see if we just plugged in 1 for x. So let's figure out f of 1. That would be 5, and let's see, that would be, oops, that should be 1. So that would be 5 over 2, which is 2.5. So here, this is 2, that's 2.5. So that's about right here. So what we're seeing is that this graph kind of rises up, and then it'll kind of turn and come back this way. So, and we'll have the same sort of thing happening there. So that's the one thing that I wanted to figure out. So we can just kind of guess that this graph is going to look something like this. So it'll probably come through like this, rise up, and then kind of do like this. And this part will come, do like this, and then eventually go like that. And so again, it's not the prettiest picture of it, but that's kind of how it goes. So now what we want to do is graph the actual slope of the tangent line, well, the actual tangent line. All right, so if we remember here, we know that the tangent line was y equals negative 3/5 x plus 16 over 5. And so 16 over 5 is just the same as 3 1/5, or 3.2. So if we come here, 1, 2, 3, so that's about right here. And so our slope tells us we need to go down 3 units and to the right to be able to find another point on that particular line. But we also know that whatever's going on here is going to have to go through this particular point. So because of the nature of this function here, we see that at some point it will actually have to probably intersect it, depending upon how it looks. So in general, and I'm just going to draw a very, very crude picture of this line, probably have a line that looks something like that. And so the idea here is not so much of, hey, this line intersects the curve, more than just once. It is the slope of this tangent line sort of follows the profile of how fast this particular function is decreasing. Okay. If you want a more accurate picture of it, then of course you can always use a calculator to do that. But in general, this is kind of how it looks. And so to give you a more realistic view of what this may look like, I'm going to erase some of this. And you'll see that this blue part here probably comes up and then just gradually goes down. Okay, so that's liable to happen as well. All right, so let's go ahead and move on to the next problem. All right, so for this example, we want to consider the function h of x, which is square root of x plus 1, and we want to find out what is going to be the derivative of f at 0, or put another way, we can find the slope of the tangent line that goes through a point on that particular graph at x equals 0. And we use that quantity to find an equation of the tangent line. So I know in the last problem we actually waited till the end to graph what's going on, but I'm going to sketch a quick graph of what is actually going on now so that we kind of understand what is going on. So here we know that square root of x plus 1 kind of looks like this. And so this is your y-axis, sorry, x-axis here, y-axis there, and of course at the point when x is 0, that will be the point 0, 1. So here, let's go through there, have this point. And so now what we want to find is the tangent line that goes through this point here. So I'll go ahead and draw that. All right, and so if we draw that, then this will kind of look something like this. And so that is what that tangent line would look like. And so what we're trying to do is find out what the slope of that tangent line would be at x equals 0. And of course, to do that, we would need to find the derivative of the function at x equals 0, which means we're going to use the difference quotient. Now, since we're dealing with a square root function, notice here that the hint that's given to us tells us that we want to use what's called the conjugate radical, of the numerator of whatever the difference quotient is going to end up being, to be able to help us rearrange what that difference quotient is going to look like so that we can actually work with it within a limit. So to get a better idea of what that actually looks like, we're going to go ahead and actually set everything up. And then from that point, you'll kind of see where we need to use the conjugate radical. So moving down here, we know that in order to find the slope of the tangent line, we need to be able to take the derivative of the function at 0, which is going to be the limit as h approaches 0 of f of 0 plus h minus f of 0, all that divided by h. Okay? Or we could write it this way. Limit as x approaches 0 of f of x minus f of 0, all that divided by x minus 0. Okay? Either option is fine. What I'm going to do is take the option of using this form of the difference quotient. So the only reason I'm using this form here is because I think we've done this other form here for previous problems. So I want to do something a little different. All right, so here if we figure out what this is supposed to look like, we'll say therefore here, we know that, if you remember, really these should be H's and not F's. So let me go ahead and change that. So my apologies on that. That should be a H, that should be a H, that should be a H, and that should be a H. And let's go ahead and change that to H's too, because we need to call the functions what they are. Yeah, and I guess for that, then it gives us a problem with the other H. Yeah. So let me just switch it back. And we'll just name that F. Yeah, so let's just call this F again. And what we'll do is this, and say that h of x is equal to f of x. So that way we have everything working how it should. All right, so we know that this is going to be square root of x plus 1. So if I was to evaluate this function when x is 0 plus h, then of course that would just be f of h minus f of 0, all that divided by h. And here we will go ahead and just substitute the first part. That would be h plus 1 minus, when we evaluated this function here at 0, that will just give us 1. And then all that will be divided by h. So now at this point, if we were going to take the limit as h approaches 0, notice that we would just end up with 0 divided by 0, which we know is an undefined or indeterminate form type case. So we can't divide anything by 0. So we need to find another way to be able to write this. And so how we'll do it is by doing what's called using the conjugate radical. And so if you remember from complex numbers, if we have an expression a plus bi, then its conjugate is a minus bi. And so in the numerator here, instead of writing square root of h plus 1 minus 1, we're going to use the conjugate radical for that, which is square root of h plus 1 plus 1, and multiply that times the numerator and denominator. So essentially we're going to take this and make this look like 1, but make 1 look like the conjugate radical of the numerator divided by the conjugate radical of the numerator. So let's go ahead and apply that now. So doing that, this will look like this. H plus 1, like that. And this will be square root of h plus 1 plus 1. Okay. So now here, when you look at this, this will look like a minus b times a plus b. And of course, a minus b times a plus b is just a squared minus b squared. And so because of that, that makes dealing with the numerator much easier to do, because we know we're going to lose these square root signs. So let's go ahead and do that now. All right, so in multiplying this, we know that if we multiply square root of h plus 1 times square root of h plus 1, then that just gets rid of the radical that we have, and we just have h plus 1. And then minus, we know that 1 times 1 is just 1. And so we're skipping all the other steps that we would normally do when we normally FOIL this, because we know that a minus b times a plus b just reduces to a squared minus b squared. So there's no need for us to do all the other things. Okay, and so here we have h times square root of h plus 1 plus 1. And so now, if we finish up, we know that these reduce, and we're here. And now these h's reduce to 1. And now what we're left with is just 1 over square root of h plus 1 plus 1. And so now, at this point, we can evaluate the limit. So from here, we have slope of the tangent line will be the limit as h approaches 0 of, and now before, remember we had the difference quotient here, but we're rewriting our difference quotient now as just 1 over square root of h plus 1 plus 1. And now, by using our limit laws and the direct substitution property, we can just plug in 0 for h there. So if we do that, we end up that, and we know that this part here just ends up being 1, so we just have 1/2. So we know that the slope of our tangent line here is just equal to 1/2. And so now that we have that, that makes it relatively easy now for the rest. We know that now we're trying to find the equation of the tangent line, and our slope is going to be 1/2. And we know we have the point 0, 1 on our graph here, because again, when we plug in 0 for x, we get just square root of 0 plus 1, which is square root of 1, which is just 1. And so if we want to do the equation of the tangent line in slope-intercept form, that would just be 1/2 x plus 1, because this by definition is a y-intercept. So this is our equation for that. And so we move on. We'll see if we illustrate this now graphically. And of course, this will be relatively easy to do because our function here kind of looks like this. And we know that this is the point 0, 1 right here. And we'll go ahead and take that point and move it there. And the last thing that we'll do is draw our tangent line. So that tangent line should look something like this.